Cool. So here we are in part 2. I was a bit... okay, so let's put it this way. I have basically recorded the lecture, or I gave the lecture in its entirety, but the computer only picked up about half of it. So sorry that first part cut off at the end. Let's go ahead and pick up where I left off there. I hope you enjoyed your break. So here's the deal. Where we left off, I was about to say something about how it was a little trickier to use the principle of inclusion exclusion when there are more and more sets that you have to deal with. In particular, if we're looking to each level of inclusion exclusion, so let me see if I can pick up an example here. Let me find one really quickly. So here was the idea from last time. So it was kind of tricky at each level. So the singleton sets constitute a level. The pairwise intersections constitute yet a second level, and then the triple intersection at the end is the third level I want to talk about. So the idea behind this is that each set within each level here had to be counted a different way, and that's just obnoxious when we're trying to use the principle of inclusion and exclusion. So what we'd like to do is we'd like to cheat this a little bit. We'd like to kind of figure out a way to get around having to go through and count each set individually. Unfortunately, that's not always going to be the case. We're not always going to be able to do this, but there are many instances where it's entirely possible for us to cheat the principle of inclusion and exclusion and not necessarily count every single set, which is a godsend when we have many different sets. When we have n up to like 10 or 20, that's a lot of different subsets that you're going to have to consider, a lot of different intersections. But if all the different levels are counted the same way, then you really only have to count 20 different things. And let's go through exactly what I mean through the following example. And in this example, let's clarify what we're asking for. So I want to know how many integers in the first 99,999,999 that include either a 1, a 3, a 7, or a 9 as one of its digits. Now, it doesn't have to be either or, so I mean it's not an exclusive or. So I very well could have numbers like 13 or 137 or 190 or maybe 379. These are all different numbers that belong to this set that I want to count. And even worse, I could have numbers like 99,999,999. That belongs to this set as well. So it's actually really tricky to count this because of the number of which numbers I would like to appear in each digit or in each number, which numbers 1 through 1, 3, 7, or 9 I would like to appear in the number, and then how many times they actually have to occur in the number is a different story entirely. So counting this directly is a bit of a bear. So what we want to do is we would like to instead use the principle of inclusion and exclusion, and we're going to do this with a certain number of properties. So we're going to do this with properties pi, where pi says about a number between 0 and 100 million. Pi doesn't have I as a digit. Okay, so this does account for all the numbers from 0 to 9, but we really only care about I equals 1, 3, 7, and 9. Cool. And from these properties, we're going to use the same old labels as usual. So label the SIs as the x's between 0 and 100 million, such that x has property pi. All right? So now we need to figure out how many total numbers are there between 0 and 100 million. Well, duh, there are 100 million. So here are the total numbers that we want. And this is the same thing as, or we'll get to what this actually equals here, but we want to think of these numbers think of these as strings of 8 digits, and those digits will come from the set of 0, 1, 2 through 9. Now, if we do that, I mean, yeah, it's kind of like an example that we did way back in the first real lecture of this course, and that would have been section 2.1. And what we're thinking about here, instead of partitioning these numbers into how many digits they have, and then using an addition principle, we're going to pad all of these small digit numbers with leading zeros. That way we can think about all of these different numbers as being strings that are 8 digits long that could lead with zeros. And if we do that, then what we're really doing is we're choosing for each of the 8 digits in the number, a number from 0 through 9. So there are 10 different choices, 8 times. Cool. So what we're going to do now is we are going to figure out how to count S1. And this one is not too hard, right? It's got to be 9 to the 8th. Now, why is that? Well, it's because we have, if we're thinking about S1 can't have 1 in it, right? So that means I can't use 1 out of these 10 digits. So I have 9 left over, and I'm making 8 choices for each, 8 choices, 9 per digit. So I wind up with 9 to the 8th. But we also notice here that it doesn't matter which digit I removed. So S3 is also counted as, okay, I'm removing the 3 from this set, but I still have 9 digits left over that I can pick, or 9 numbers I can pick in each of the 8 digits. And there go the lights. No lights, come back. Cool. So there are still 9 to the 8th different choices here, and again, I can do this for S7. I can do this for S9. No problem whatsoever. Cool. So now that we have that, sorry, one second, I'm looking for my recording bar. It disappeared on me. It shouldn't have disappeared on me. Anyway, yeah, give me 1 second to find it. It's floating around on this desktop somewhere. La la la, there it is. Hello, little recording bar. Okay, so now that he's back, I'm gonna go ahead and slide him off to the side. Oh, good news, the video is still recording. Yay, okay. So, now that we're all set again, okay, so that's how we count all the singleton sets. Now we're going to go ahead and count the pairwise intersections. So I'm going to count all the numbers that have neither a 1 nor a 3 in them. And the way we're going to count that, I'm going to remove the 1 and the 3 from the set of digits I can use. So now I really have 8 choices for my 8 digits. And this is the same thing for all of my other pairwise intersections. Right? It doesn't matter which two digits I removed, I still have a collection of 8 options per slot, per digit. And this, I will finish up writing, there are 6 different subsets, or 6 different intersections that I can use here. And they're all counted the same way. And one more. We'll count the triple intersections, and I'll just denote them SI, SJ, and SK, because I'm using the same idea. I'm removing, instead of 2 now, I'm removing 3 digits from that set. And that'll leave me 7 choices for my 8 digits. And then the final quadruple intersection is S1, S3, S7, and S9. I removed 4 numbers from that set, so I have 6 choices for my 8 digits. Now, if I'm going to use the principle of inclusion and exclusion, I need to know what these sums look like. The singleton sets here, let me move the computer around. Okay. The singleton sets are all counted the same way, and I ask myself, how many different sets were there? Well, of the 4 properties that I had at the top here, I'm really just choosing one of them and then counting, or I'm asking myself how many different ways I can choose one of them. So there are 4 properties, and I'm choosing one of them, and these are all counted exactly the same way. There's my 9 to the 8th. So now we have singleton sum being that. The pairwise sums, this is just shorthand. Of my 4 properties, I'm counting the number of ways I can choose 2 of them, and they're all counted the same way. Similarly, I get all my triple intersections, Sj, Sk, and there are 4, choose 3 different ones, different triple intersections, and they are all counted the same way as well. And my quadruple intersection, S1, S3, S7, and S9 together. Well, there's only one way to choose that. So there's 4 properties. There's 4. Choose all 4 of them, and I'm going to count that one set. I'm going to count all those different ways in 6 to the 8th. As 6 to the 8th. Okay, so then the principle of inclusion and exclusion. So finally, the PIE says that the number of different, the numbers that I want to include in my set are take all the total numbers that I could have, subtract off the sum of the singletons, so that's 4, choose 1 times 9 to the 8th, add back on the pairwise intersections, and these guys are all counted the same way, subtract out the triple intersections, and then add back on the quadruple intersection. And that's it. And notice here there's a 4, a 3, a 2, a 1. It would stand to reason that there is one way to choose no properties, and that's my 4 choose 0. Pretty nifty, right? Now, here's the deal. This number comes out to about 7,096,824. This is approximately 7.1% of the numbers in U. So in other words, this is actually a pretty small proportion. I'm looking at all the numbers that don't contain one of these 4. Or principle of inclusion exclusion makes me count all the ones that do have one of these 4 numbers in it. Now, that's 4 out of 10 different options here. That's something like 20% of the digits I could, or 20% of the choices I have. No, 40% of the choices I have. I can math. There's 40% of the choices I have, and yet there's the numbers that have those digits in them are only comprising about 7% of the total number of all the numbers between 0 and 100 million. So that to me seems odd. So it's a little counterintuitive. But at the same time, there are lots of different ways that I can include either a 1, a 3, a 7, or a 9 in my number. But what this is telling me is that there are vastly more ways for me to not include them in my number. So it's kind of interesting that this is the kind of result that we see out of a generalized subtraction principle, that there are things that we just didn't consider, or maybe that we are kind of overlooking when we're using our general intuition behind a problem. All right, so that about does it for section 6.1. And we're going to continue into section 6.2 by talking about combinations with repetitions again. So we're going to be talking about multi-set combinations, but with a bit of a twist. So these were relatively easy to compute, right? If I'm asking for the number of 10 combinations of some multi-set, you can tell me, provided though, easy to compute. So provided, these are easy to count provided there's an unlimited supply of each type of number, or each type of element. An unlimited supply of the elements. So the repetition numbers are sufficiently high, or maybe say sufficiently high. Okay? Now, these were the solutions to this equation, the integral solutions to this equation, provided I very well could have imposed a certain number, like I require each xi to have a certain number of elements in the combination, and this it's still going to be the same sort of solution as with the non-negative solutions case. But this will amount to some number, choose some number of dividers, and then plus some number of dividers, and then choose where you want to put the dividers. But now I'm going to put a wrinkle in this. You saw at the end of your first homework when we wanted to ask for the n combinations of the following multiset, where we had n a's and one each of the numbers 1 through n. All right, so this we can also translate into an integral equation, but there is something interesting that happens here. So here's the number of a's we'd like to include in our n set, the number of 1's, the number of 2's, all the way out to the number of n's, and we want to make sure we have n total. And x dot, I'll say, each x has to be non-negative, but we're also going to impose the restriction that the numbers here, the xi's, can't exceed 1, right? Because I don't have an unlimited supply of these. That's what made this problem so much different to count, so much trickier to work with. We're going to see in this section exactly how to use the principle of inclusion and exclusion to answer exactly this problem. But we need to go back to how in the heck are we going to compute this when we have a cap on it? Well, you come back to this case where, yeah, it's a lot easier to count the case when there's an unlimited supply, regardless of having to include a certain number. As long as there isn't an upper bound on these numbers, then this is actually a relatively easy problem to count. So we need to find a way of getting rid of these upper bound restrictions, and this is exactly what the principle of inclusion and exclusion is going to do for us. We are asking for the property not xi less than 1, less than or equal to 1, and this is the same thing as xi being at least 2. So we've now, instead of looking at the upper bounded case, we look at strictly the lower bounded cases. And it's perhaps easiest to see what I mean here about how this is trickier in general when we have the upper bounds. And not to mention, it might be a good idea to have a complete list of a particular example so we know we're actually on the right track. So how many 3 combinations are there of the multiset S, which is comprised of 1A, 2 B's, and 3 C's? We can actually list out exactly what they are, and this isn't too hard to do. This is A, 2B, A, B, and C, 2 B's and a C, A and 2 C's, and then finally 1 B and 2 C's. And there are five of these in total. Cool. And you can check that this is exhaustive, and you can think about choosing the 3 combinations as taking away from this set of 5 things exactly 2 of them. And then what's left over is your 3 combinations. Now, the problem there is that you're going to have to take away, 2 C's, not 3 C's. If you think about taking away as many C's as you want, so take away 2 C's, great, you can construct a subset there. It's this guy right here. If you take away the 2 B's, then yeah, you go ahead and get an A and 2 C's. That's this fellow here. But you can't take away 2 A's. Any combination that uses an A has to use a B or a C. And the fact that when we move from type to type throughout this list, and we have to count them differently, that's what makes it hard to count these subsets directly. It's because there's a myriad different options of how you can include or exclude elements from a set or from a subset, and well, frankly, we'd like to avoid doing casework. So first, we should probably frame this question in terms of one of these integral equations. So it's not too hard to see. We can reframe this as the following equation, or the equation x1 plus x2 plus x3, where I want to make sure I have exactly 3 elements in my subset, and I make sure that x1 has no more than one thing in it, and x2 and x3 contribute no more than 2. Okay, so this problem is, the answer to this problem is the same count that we're going to get for this problem. So we should expect to see 5 here. Let's go through and count this using inclusion and exclusion. So name some properties here that force us to kind of negate or break these rules on the upper bounds. So we're going to name P1 the property that x1 is at least 2. So we're going to break that bound. We're going to go past 1. We're going to name P2 as the property where x2 is at least 3. And P3, take a guess. That's right, those of you who shouted at your computers. x3 is at least 3. So then we use the PIE to count complements in some sense. So we're going to count all the ways where we don't satisfy these 3 properties. And count complements. And we're going to look at these sets SI, where X belongs to U, and I'll tell you what U is in a moment, because the universe isn't quite what you think it is in this problem, so I'll make sure to really clarify that. Make sure that X satisfies PI for each SI. That's how you define the SIs, as usual. Where, let's see, I'll try to cram it up here, where U is the set of 3 combinations, not of this set right here, but rather of the set with no restrictions on it. So I'll call it S star, and these are the unlimited. Oh, the lights are killing me. Come on, lights, wake up. Okay, looks like the video's still going. So we're not going to use this subset upstairs. Instead, we're going to use the unlimited supply subset, infinite B's and infinite C's. Let me make sure it's on the screen. There we go. So we're going to count from these, the ones that have no limitation on them whatsoever. We're going to count the ones that actually break our restrictions, and then we'll subtract those off of the count and get what we need, the ones that satisfy the opposites of these properties, the ones that don't satisfy any of those 3 properties. So let's go ahead and first count S1. Now, S1, these are all the solutions, all the 3 combinations. So I'm looking at x1 plus x2 plus x3 such that they all equal 3. And I want to make sure that I satisfy property 2. So that's x1 has to be at least 2. But then x2 and x3, remember, I don't have any restrictions on these sets anymore because I'm not counting the unlimited case. Uh-oh, my screen froze here. This is not good. Come on, wake up, screen. Oh, what happened to the live image? No. No. Uh-oh. Uh-oh. Okay, and we'll be back shortly.